Hello students, let us continue our discussion on current electricity. Today we are going to take few more problems from question number 11, page number 150. Okay, question number 11 is as follows. When two resistors are connected in series with a cell of EMF 2 volt and negligible internal resistance, a current of 2 by 5 ampere flows in the circuit. When the same two resistors are connected in parallel with the same battery, the same of 2 volt, the main current is 5 by 3 ampere. Calculate the resistances. So in this problem, we have two situations given. In the first situation, and before we enter the situations, we should know that there are two resistors given here, and both the resistors may not be equal to each other. They are two different resistors because they have not mentioned anywhere here that the resistors are equal. So we have to assume two unequal resistors now. Let me take the two unequal resistors as R1 and R2. Okay, R1 and R2 be the resistances that we have. Now this R1 and R2, when they are connected in series, okay, the first situation is series situation. When these two are connected in series with a cell of EMF 2 volt, okay, we are connecting the combination with a cell of EMF 2 volt and negligible internal resistance, which means this cell does not have considerably good resistance, so it is negligible. And the resistances here are R1 and R2. Okay, so this is the first situation. In this situation, the current through the circuit is observed to be 2 by 5 ampere. Okay, clear? So this is what is given in this part till here. And now when the same two resistors are connected in parallel, okay, the very same two resistors, when they are connected in parallel, R1, R2, with the same battery, okay, of 2 volt, then the main current means here from the battery, drawn from the battery, okay, not in the branches but from the battery itself. So the main current in the circuit is found to be 5 by 3 ampere in this situation. Now R1 and R2 has to be found. So this is the question. Now we have to work for R1 and R2. Now let me take the first circuit and get the effective resistance. Since the combination is series, I can get Rs is equal to R1 plus R2, right, for the first situation. Similarly, writing the expression for the second situation, I can write Rp is equal to R1 R2 by R1 plus R2. Okay, so this is the expression for the second situation, parallel combination. Now Rs is the effective resistance, right? So this first circuit now can be visualized like this, right, with this single resistance Rs with the same voltage and the current 2 by 5 ampere. This is how I can visualize the same circuit. This circuit is visualized like this because I have replaced R1, R2 in series by Rs. In the same way, I can replace this R1, R2 in parallel by a single resistance Rp and rewrite the circuit like this. 2 volt is the battery and the current is 5 by 3 ampere. Okay, now the circuit has reduced to the effective circuits. And Rs and Rp, if we can get Rs and Rp, then we can obtain R1 and R2, right? We'll get few simultaneous equations and we can get it. So let us work for Rs and Rp now. Okay, from the first circuit, okay, you can observe here that upon applying Ohm's law, we have V is equal to IR. V is equal to IRS this time, the series one. So RS becomes equal to V by I. What is V? 2 volt. What is I? I is 2 by 5 volt. 2 and 2 cancels, and hence we have RS is equal to 5 comes to the numerator, 5 ohm. Okay, so this is one important result, but not the final answer. Final answer is R1 and R2. They are the final results, but this is an important intermediate result which will help us in getting the values of R1 and R2. Now coming to this part, in the same way, V is equal to I RP this time, right? From this expression, RP becomes equal to V is 2 volt again, and the current is 5 by 3 amperes, right? Is it right? Yeah, the current is 5 by 3 ampere, and hence RP becomes equal to 3 goes to the numerator and hence becomes 6 by 5 ohm. Okay, so this is what is RP. Again, this is not the final result. These are the intermediate results which will help us in getting R1 and R2. The final results that we need are R1 and R2. Right. So let me put RS here. If I put RS here, the value of RS here, I get R1 plus R2 is equal to 5. And if I put RP, the value of RP here into this equation, I get 6 by 5 is equal to R1 R2 by R1 plus R2. But what is R1 plus R2? R1 plus R2 is 5, right? From this, so I can write 5 here. So 5 and 5 cancels, and hence I will be left with R1 R2 is equal to 6. Do you remember this kind of problems? You have already solved this kind of problems in 8th and 9th standard itself. 8th I think in maths. So you have two values A and B. The product of them is given and the sum of them is given. You have to get those values. Okay, the similar kind of problem now we have here. Quite simple. You can make use of approximation here. Okay, one way, and the other way is you have R1 plus R2. You get R1 minus R2 using these values. Okay, so you can make use of approximation. That is also a valid method. You can directly write by approximation R1. Okay, what are the possible values of R1 and R2? If I give R1 is equal to 3, R2 is equal to 2, then R1 plus R2 will become 5 and R1 into R2 will become 6. So I can directly write by approximation R1 is equal to 3 ohm and R2 is equal to 2 ohm. Okay, this is a valid method. But if you want to be, if you don't get this kind of easily available values, then you can go for finding R1 minus R2 using the formula R1 minus R2 whole square is equal to R1 plus R2 whole squared minus 4 R1 R2. Using this, you put R1 plus R2 value here, R1 R2 value here, square this and simplify. After taking the square root, you will get R1 minus R2. Okay, after simplification. Once you have the value of R1 minus R2, and here you have R1 plus R2, you can add those two equations and get the value of R1 and hence R2. Okay, you can make use of this form when you do not directly get, when you don't get the values of R1, R2 directly by approximation. Okay, and the method is detailedly given in the reference. Make use of that. Clear? And hence we have obtained the values of unknown resistance R1 and R2. Clear? Okay, the next question, 12th one, is as follows. The resistance coils, which means resistances, Okay, the resistance coils of 100 ohm and 200 ohm are connected in series across 100 volt supply. A moving coil voltmeter of resistance 200 ohm is connected in turn across each coil. What will it read in each case? Okay, so this question seems to be a bit different for you, but do not worry about this moving coil galvanometer, moving coil voltmeter term. Okay, because we are going to study this moving coil voltmeter in detailedly in the coming chapter. But for now, I can say this much, that voltmeter is a device which measures the potential difference across the terminals across which it is connected. Okay, the potential difference or the voltage is measured. It's a device to measure voltage. And remember, every electrical device has its own resistance. So even this voltmeter connected here has its own resistance. How much is that? It is of 200 ohm resistance. And basically the structure is as follows. The basic circuit is the same. We have two resistors. Okay, one is 100 ohm and the other is 200 ohm connected in series, right? Across what? Across the supply, power supply of 100 volt, right? So this is the situation now. And then they connect a voltmeter, okay, voltmeter of resistance 200 ohm is connected in turn across each coil, which means they connect the voltmeter first with one of the coil here, and in the next situation they remove the voltmeter from here and connect it across 200 ohm resistance. Okay, so this is the first situation now where they have connected a 200 ohm resistance voltmeter in across the 100 ohm resistance, and now we need to calculate how much this voltmeter reads. Okay, how much will the voltmeter read? Voltmeter reads what is the potential difference across these 2 points. Okay, it always reads the potential difference. So now what we need to calculate is the voltage across this combination. Okay, across this resistance or this combination, I can say. So if I can get the voltage across this 100 ohm resistance, then that will give me the reading of voltmeter. Okay, similarly in the next situation, if I get the voltage across this 200 ohm when it is connected here, then that will give me the reading of the voltmeter. Okay, voltmeter reads what is the voltage across these 2 points. So our intention now is to get the voltage across these 2 points. Okay, let us work for the voltage now. Now you see, what we need is voltage across these 2 points. But we have very less data with us, because if I have the current flowing in the entire network, okay, then since this voltmeter's resistance and this resistance 100 ohm are in parallel, I can get the effective resistance. Once I have the effective resistance, then I can easily get current will be here. Potential difference can be obtained, okay, using Ohm's law. Now in the first place, what we need is the current flowing through the entire network. Okay, so we should first work for the current flowing through the network, because current will give us the idea, or current will give us the mathematical connection between the voltage and the resistance. Okay, so let us work for the current through the circuit now in this situation. First of all, the effective of these two, since this has also got certain resistance 200 ohm and they are in parallel combination, let me put Rp is equal to R1 R2 by R1 plus R2. This I am introducing this formula because this voltmeter has a resistance of 200 ohm and this voltmeter is connected to 100 ohm external resistance. Now both of them in parallel gives us certain effective resistance, and that effective resistance is calculated now, which will be equal to 100 into 200 divided by 100 plus 200. So which is 100 into 200 by 300. Zeros cancels. So it's 200 by 3. Okay. So this is the effective resistance of the combination. 200 by 3. You can simplify it. It will be 66.666. So this is the resistance here, and with this resistance, with this effective RP, we have one more 200 ohm resistance connected in series. Okay, because if I want the total current, I want the total effective resistance. So in the reference they have directly added that here, but I'll do it separately now. So RS finally is equal to this RP. Okay, this is this together is RP plus this resistance. Okay, if I call that as R3, then RP is 200 by 3 plus 200 R3. Now this will give me the entire resistance, the total resistance of the network that we have. So it is going to be 200 plus 3 by 200. Take the LCM. So it is 600 plus 200, 800 by 3 ohm. Okay, 800 by 3 ohm is the resistance of the entire network. So now this is the effective resistance, the total resistance, and the total voltage supplied is 100 volt. Current has to be found. Okay, so again using Ohm's law for the entire network. Ohm's law. If I name this as points A, B, C. Now I am applying the Ohm's law between the points A and C. Okay, across the battery. Ohm's law for AC or between AC, A and C. Okay, here voltage across it is 100 volt. The formula says V is equal to IR. Voltage across that is 100 volt. Current has to be found, and the effective resistance, the entire effective resistance is found to be 800 by 3, right? I is equal to V by R. So these two zeros cancels, 3 goes to the numerator, and hence the current through the entire network becomes 3 by 8 ampere. Okay, so the current through the entire network is 3 by 8 ampere. Now this current will help us in getting the voltage across these 2 points A and B. Okay, let us work for the voltage across A and B now. Voltage across A and B. Right. See, when we come to voltage across A and B, again we will make use of Ohm's law, which is V is equal to IR. Now, these are the 2 points. What is the current flowing through this parts A and this current flowing between these 2 points A and B? The current flowing will be same, 3 by 8 ampere, because I am considering this as an effective circuit. Okay, or this two combination, the parallel combination is considered as one resistance. So this is RP here and this is R3. Okay, so between A and B there is a single current flowing, which is 3 by 8 ampere. Okay, between A and B. Don't worry about the branches, because I am considering these two together as one resistor of resistance RP. Okay, so now RP here. So voltage across AB, okay, let me name that as voltage across AB, is equal to current through AB is 3 by 8 ampere into resistance across AB. Okay, resistance across AB is this one, 200 by 3. Following? 200 by 3. Simplify that, and hence you will have voltage across AB given by 25 volt. Okay, clear with this? So what we were supposed to find is the reading of the voltmeter when it is connected across 100 ohm. Now we have connected it across 100 ohm. This voltmeter itself has its own resistance now. So, and the voltage across these 2 points, when we take these 2 points, there are common points for both voltmeter and this 100 ohm resistance. So voltage is same for both of them. I will consider them as the combination of 2 resistors here, the parallel combination, and I obtained the effective resistance Rp of the combination given by 200 by 3. Okay, then I add this combination with this other resistance in series. So now Rp plus R3 will give me the resistance of the entire network, and that is 800 by 3 ohm. Now when I apply Ohm's law between A and C, voltage is given 100 volt, that is the supply, and between A and C the effective resistance is found 800 by 3, and now the current will become 3 by 8 ampere. Okay, so what we have now here is the current through the entire network, which is 3 by 8 ampere. Now you have current through this part of the network, or now I am considering 2 points A and B. Current through this part of the network A and B is same, 3 by 8 ampere, because I am considering this as combination, okay, not the separate one. Okay, so 3 by 8 ampere, 3 by 8 ampere, 3 by 8 ampere, 3 by 8 ampere. So 3 by 8 ampere is the current, and between A and B voltage has to be measured. Okay, whatever the voltage that we get across A and B, between A and B itself is the reading of the voltmeter. Okay, that is what voltmeter reads. So between A and B voltage has to be found. Between A and B the current is 3 by 8 ampere. Between A and B the resistance is Rp, because there are only 2 combinations and the 2 resistors. So Rp is 200 by 3, I is given, and hence VAB, okay, voltage across AB is found, which is 25 volt. Okay, now it's time to work the similar way for the second resistance. Okay, now the change that I'm going to make is I'll remove the voltmeter across A and B, and I'll connect the same voltmeter across B and C, which means with the second resistance, because see, the voltmeter of resistance 200 ohm is connected in turn across each coil. In the first turn they connect it across 100 ohm coil, in the second turn they connect it with 200 ohm coil. Okay, that is what it means. So we are now connecting it to a 200 ohm resistor. Okay, now once again now the current will be different because the combination has become different, but we are connecting it to the same battery. Okay, same power supply. So the same approach, first we need to get the current through the entire network. Okay, the main current drawn, and that same current will be flowing through this 100 ohm and this combination and coming back. So in order to get that, we need the effective resistance. So now this voltmeter and 200 ohm resistor are in parallel. So across B and C, okay, across B and C, Rp is equal to R1 R2 by R1 plus R2. Since they are same, I could have directly taken as 200 by 2, that it be 200 into 200 by 200 plus 200. So this is going to be 200 into 200 by 400. Okay, when they are equal, I can directly take the effective resistance as half of them. Okay, that I can do. So 2 ones are, so 100 ohm. Okay, 100 ohm is the effective resistance of this voltmeter's resistance and this 200 ohm resistance. Okay, now this combination is connected with 100 ohm resistance. So it is in series RS. The entire network is now this Rp plus, now I'll name this as R3 now. Okay, Rp plus R3. See, now I have considered this as R1, this as R2, and this as R3. Okay. So RP is how much? 100 ohm plus. R3 is, RP is 100, R3 is 100. So it is 200 ohm of resistance from the entire network. Now what we are interested is current through the entire network. So applying Ohm's law between A and C again, between A and C, V is equal to IR, I is equal to V by R. What is the voltage across AC? Voltage across AC is 100 volt. That is what is supplied. What is the resistance across this AC? Resistance across this AC is the combination of all this, which we have obtained as 200 ohm. So the current becomes half ampere, 1 by 2 ampere. Okay, that's the main current. But what we need is voltage across B and C. Okay, now we will work for voltage across B and C, because this is the voltage which the voltmeter will show. So voltage across B and C. Again, we will make use of Ohm's law, which says V is equal to IR. This time voltage is measured across BC. Current through the network is half ampere. Okay, the same current will flow through the combination, okay, together. Here the current will split at this point. Current will split, half ampere will split, since they are equal, 1 by 4 ampere. Okay, 1 by 4 ampere will go here, 1 by 4 ampere will come here, but together they will join and become half ampere again at point C. And what we are interested is between point B and C. When I take the points B and C, the main current, okay, if I take point B here and point C here, the current here and here are important for me, and these two currents are the same current which is in the main current in the circuit. So this current, because this I have considered as the combination, okay, as a combination I have considered. So between point B and C, the total current flowing is same as the main current, which is half ampere, into the resistance is the effective resistance of these two in parallel, which is RP, which is 100 ohm, which we have already calculated. So voltage across B and C now is equal to 50 volts. Okay. So from this, we got to know that when the voltmeter is connected across 100 ohm resistor, it reads 25 volts. When the same voltmeter is connected across 200 ohm resistor, it reads 50 volt. Okay, clear with this? Right, the next question, 13th one, is on a battery, which includes the internal resistance of the battery. Okay, this is the first time we are taking such a problem, and it's a simple one. The storage battery of a car has an EMF of 12 volt. If the internal resistance of the battery is 0.4 ohm, okay, internal resistance given, what is the maximum current that can be drawn from the battery? Okay, now, okay, look at the situation here. What we have here is a battery, okay, and this battery has the EMF of 12 volt and the internal resistance of 0.4 ohm. Now, when do we get the maximum current out of this battery? Think of it. See, when do we get the maximum current? When we have no resistance externally connected, then we can get the maximum current, isn't it? Any resistance introduced here externally will reduce the current in the circuit, right? Because resistance always opposes the flow of current. So the current will be reduced if I introduce an external resistance. If I do not have any external resistance in the circuit, then I can draw maximum current from the circuit. Clear with that? Now, if in an ideal situation, if the battery also does not have any internal resistance, then I can get infinite current using any battery that I have. But that's an ideal battery. In normal situation, every battery will have its own internal resistance, and hence I cannot get infinite current. Understood? So maximum current can be drawn. Okay, maximum current can be drawn from the battery when the external resistance, okay, remember the simple circuit, you have simple internal resistance here and external resistance, and that external resistance is always represented by capital R, right? When the external resistance is 0 ohm. Okay, clear with the conceptual part? When we have no resistance externally connected, we can get the maximum current. Okay, now how much is that current? So the current formula is given by I is equal to EMF E divided by R plus R. Okay, this is the formula of current through a circuit, current through a resistor capital R, when you have the battery of EMF E and internal resistance small r. Okay, you should remember the formula. Now, what is the value of E? The EMF is 12 volt. In order to get the maximum current, we have made the external resistance 0, and the internal resistance of the battery is 0.4 ohm, and hence I have the current given by 12 by 0.4, which is equal to 120 by 4, 30 ampere is the maximum current that can be drawn using this battery. Okay, clear with the concept first? When there is no external resistance, we can get maximum current in the circuit, so we made capital R 0, and the formula for current through this kind of simple circuit with a battery and an external resistance is I is equal to E by R plus R. We made use of that to get the current through, the maximum current that can be drawn using this. Okay. Okay, the next question number 14 is as follows. A storage battery of EMF 8.0 volt, 8 volt, okay, and internal resistance of 0.5 ohm is being charged by a 120 volt DC supply using a series resistor of 15.5 ohm. What is the terminal voltage of the battery during charging? Okay. What is the purpose of having a series resistor in the charging circuit? So this is about a battery getting charged. Okay, this is a new kind of question for us. Right, let me draw the circuit first. Okay, how does the circuit look like? Here we have a battery getting charged, and this battery has another resistor in series with it. Okay, and both of them are connected to external supply of 120 volt. Okay, this is somewhat like charging your charging the mobile phone you use in a train. Okay, normally the plugs that we have in train are of DC. Okay, they mentioned there 120 volt DC, 100 volt DC, and we are trying to charge our mobile phone. Okay, this is the battery of our mobile phone, and this is another resistor connected, somewhat like that. Okay, but the simplest circuit is this 120 volt supply connected to a battery recharging, and this battery has the EMF of 8 volt. Okay, this battery has the EMF which we normally represented by small e. Why? Because capital E is the total EMF of the circuit, and small e is the EMF of the battery which is getting charged. And this battery has the internal resistance of 0.5 ohm. Okay, so small r is equal to 0.5 ohm. This is the nature of the battery. 8 volt EMF, 0.5 ohm internal resistance. And the external resistance connected in series, let me name that as capital R, which is equal to how much? 15.5 ohm. Okay, and this is the total voltage across both the battery and the resistor. So writing the given data separately, I have the EMF of the battery getting charged. Okay, we always represent the EMF of the battery getting charged using small e. Okay, and the total EMF of the network is considered as capital E. Okay, small e is 8 volt and internal resistance is 0.5 ohm, and the external resistance in series with the battery is 15.5 ohm, and the voltage supplied to the entire circuit is 120 volt. Okay, these are the given data. Then what is asked to find? What is the terminal voltage of the battery during charging? Which means now we need to get the voltage across these 2 points. Okay, if I name them as A, B, C, I have to now get the voltage across A and B. Okay, that is what is asked. Terminal voltage of the battery, voltage between A and B, so across battery, which has to be found. So what is to be found? VAB is equal to question mark. Clear with this? Okay, so now before moving ahead, we should be aware of how to get the voltage across these 2 points A and B. Voltage is not as same as the EMF. EMF is different, voltage is different, right? EMF is when the circuit is in open condition, but here the circuit is closed, the battery is getting charged. So here we get TPD, terminal potential difference, across A and B. Now the points A and B are the terminals of the battery, and hence I can get the voltage across A and B to get the potential difference or voltage across the battery. Okay, right. In order to get the voltage across A and B, we are going to make use of same method which we made use of in the previous problem. First we will get the current in the entire network. Okay, and hence then we will multiply that current with the internal resistance of the battery. Okay, and hence we'll get the voltage across A and B. So first we should get the current in the circuit. Okay, we should aim to get the current in the circuit. Now, in order to get the current in the circuit, we should first have the effective EMF of the circuit, which is capital E. Now, what is the relation between the effective EMF of the circuit, capital E, and the EMF of the battery getting charged? There is a relation which is given by E is equal to V minus E. Remember this. So E is the effective EMF of the entire network. V is the voltage supplied. E is the EMF of the battery which is getting charged. Okay, so now the EMF of the entire network can be obtained using this formula. We have 120 volts supplied, minus E, it is drawn from the circuit, which is 8 volt, and hence the EMF of the circuit left is 112 volt. Okay, so our intention was to get the current in the circuit. In order to get the current in the circuit, we should first have the effective EMF of the circuit. Effective EMF of the circuit is given by E is equal to V minus E, where V is the voltage supplied, E is the EMF of the battery getting charged. Using that, we obtained E now. Now our intention is to get I. What is the formula of I when we have a battery and EMF and all like this, it's I is equal to E by R plus R, the familiar expression. Now E is the effective EMF. Okay, remember this, since we have considered the battery getting charged. E is the effective EMF and R is the external resistance, small r is the internal resistance of the cell or the battery. So E is 112 divided by capital R, the external resistance connected is 15.5 plus the internal resistance of the battery is 0.5. Okay, and hence we have current I is equal to 112 by 16. And after simplifying this, we'll get the current is equal to 7 ampere. Okay, so 7 ampere is the current that is flowing through the entire network, like this. 7 ampere current is flowing. What they have asked us to find is the voltage across A and B now. Okay, now voltage across A and B is not that easy to obtain because this involves a battery or a cell getting charged. Instead, what we can do is we can get the voltage across the points B and C. Okay, I'll tell you why. Because once we have the voltage across B and C, the total voltage across A and C is known to us. Total voltage across A and C is 120 volt, right? So if I can get voltage across BC, then voltage across AB plus voltage across BC is the voltage across AC, right? We can make use of that. So let me work for voltage across BC now. Okay, voltage across BC using Ohm's law, V is equal to IR. Okay, current through the entire network is can be found, which we have obtained as 7 ampere, and the resistance that we have is 15.5 ohm, and hence voltage across BC is obtained to be 108.5 volt. Okay, so this is the voltage across BC. Okay, but what we know is voltage across A and C. Okay, voltage across A and C. Okay, let me write it here itself. Observe carefully. Voltage across AC is equal to voltage across AB plus voltage across BC, right? What is the voltage across AC? 120 volt supplied, so it is 120. What is voltage across AB, which has to be found? That itself is what is the final result required, plus what is voltage across BC? It is 108.5, and hence voltage across AB is equal to 120 minus 108.5, which is VAB is equal to 11.5 volt. So VAB is the voltage which is 11.5 volt across the battery given. Okay, so one thing is clear, that we have obtained the terminal voltage of the battery is found now. Okay, so whenever they ask to find the voltage across any electrical component, we always look in this direction to get the main current in the circuit. So here also we did the same approach. Main current in the circuit has to be found. How do we find the main current? Here it involves a power supply and a battery getting charged. So whenever you have a power supply and battery getting charged, you should have effective EMF. Okay, whenever you have a battery with internal resistance, we should go for EMF itself to get the current, right, with the internal resistance when we have. So E is the effective EMF, which is given by V minus E, where V is the supply, voltage supplied, E is the EMF of the battery getting charged. Using this, we obtained the effective EMF of the network to be 112 volt. And we made use of that in the formula I is equal to E by R plus R to get the current, which is 7 ampere. So 7 ampere current flows through the entire network now. And this 7 ampere current is flowing through both the battery and the external resistance. Now, we went to get the voltage across B and C first. Because getting the voltage across B and C is simple, because what we have is a simple resistor here. So we applied Ohm's law between B and C. Between B and C, current flowing is 7 ampere. Between B and C, the resistance is 15.5 ohm. Between B and C, the voltage is taken as VBC, and we obtained the voltage across B and C as 108.5 volt. After getting the voltage across BC, we went for the voltage across AB, because the effective voltage between A and C, VAC, is equal to VAB plus VBC, right? We know what is VBC, we have calculated it, and we do know what is VAC. That itself is the power supply, which is 120 volt. So 120 is equal to VAB plus 108.5. So after simplifying, we have VAB given by 11.5 volt. Okay, that is the voltage across the battery, the cell given. Now, what is the purpose? This is the first part of the question answered. This will cover, like, if it is in board exams, you have 4 marks with you. The last mark is what is the purpose of having a series resistor in the charging circuit? Why do we need this resistor here? What is the necessity of the resistor? Okay, the reason being, if we do not have this resistor, in the absence of this external resistance, the cell, okay, or did we name it as cell or battery? Battery, yes. Okay, in the absence of this external resistance, the storage battery will draw huge current from the source. Because see, from this here, if you make capital R is equal to 0, then what happens is 112 by 0.5. What is 112 by 0.5? 224 ampere of current. That much of current is too high to charge a battery, and the battery will get damaged. We don't want that. Okay, we always want small current to charge the battery. That because that depends on different batteries. And in this situation, in order to avoid dangerously high currents flowing through the storage battery, we require an external resistance connected in series with the battery getting charged. Okay, so that is the reason why we need an external resistance connected. Thank you.